Today, we're going to do several experiments so you can finally understand once and for all what quantum physics is. We have an illustrious guest here, Alfredo Luis Matias, our great friend, who co-wrote with me 50 experiments to do at home. By the way, Alfredo, I just found a photo of you here with black hair.
Wow, that was quite a while ago, huh?
We wrote that book back in 2014, but it's still one of Manuel do Mundo's bestsellers. Lots of people have made a mess at home with that book, and they're still doing it and learning a lot, which is what really matters, right?
It's packed with cool experiments. Yeah, stuff you can actually do at home.
Yeah, things you can buy at the supermarket and figure out right in your own house. So, Alfredo, to kick things off, what is quantum physics?
The idea here, Iber, is that 2025 was chosen as the International Year of Quantum Science and Technology, right? It was designated by the United Nations. People don't really know what quantum physics is, do they? People hear that word, and lots of folks use it incorrectly. There's a ton of quantum scams out there, right?
Quantum medicine, quantum water, who knows what else, right?
Quantum consciousness, right? They try to make it sound esoteric, but none of that's real. Quantum physics is a science, okay? It's a way for us to model and understand what's happening inside atoms, in things that are extremely, extremely tiny.
In things we can't see even if the cow coughs.
No, you really can't see them. They're incredibly small, and precisely because they're so tiny, they're hard for us to understand. So there's a whole long history how humanity came to understand that atoms exist and what's inside them, how the atom was structured. And we've brought along a bunch of experiments that explore exactly that.
Let's get started then.
Look here, Iber, you have no idea what's underneath this board, right? No, there's something here. But how are we going to find out? You'll discover it by taking these marbles and rolling them down this ramp.
Down this ramp,
Right? And now we saw where it went in and where it came out.
Right?
And we'll mark it here with this mark. But now we'll do it again. We'll shift it over a bit and roll another marble.
This one went straight through.
Went straight through.
Which means the object isn't here, the board isn't along this line.
Exactly. Let's roll another one.
Went straight through again. Whoa, this one did that?
It hit and bounced back.
I already know there's something here.
Right? Let's drop a few more just to see if...
Just to be sure. Whoa, look at this one.
Hit it right on the corner. Here's the idea. Can you roughly guess the size of whatever's underneath there?
I can. If there's something roughly around here like this.
Exactly, because the marble's hitting it, bouncing off and coming back. This is a mechanical analogy of an experiment conducted by a scientist named Ernest Rutherford. He did it with his students, but in a completely different way. He didn't throw marbles instead. He used a radioactive material that emitted alpha particles, heavy, positively charged particles.
Kind of like protons there.
Right, today we know they consist of protons and neutrons, 2 protons and 2 neutrons. Back then, he just called them alpha particles, and he knew they were positively charged. And what he did was fire them at a sheet of gold. Extremely, extremely thin gold. They kept hammering it thinner until it was only 400 atoms thick. And then what happened? He couldn't see the path of each alpha particle, but he placed a phosphorescent material there. We'll talk about phosphorescence in a bit, but every time an alpha particle hit the phosphorescent material, it produced a flash of light.
So he could basically do what we just did here. He'd fire a particle, and if it deflected, he knew something wasn't.
He'd move the detector around.
There's something weird going on.
He placed that phosphorescent material all around and measured. At this angle, how many alpha particles arrived? At that angle, how many arrived? And he went all the way around. And what did they expect to happen? They thought virtually all the alpha particles would go straight through.
But they didn't all go through.
Some actually hit and bounced back.
Just like here.
Just like here, right? Not only did many deflect significantly, but some even bounced straight back toward the side where the radioactive source was. Rutherford was completely shocked. He said, "It's as if you fired a cannonball at a sheet of paper and the cannonball bounced right back at you." That's basically what it felt like, and he never expected it to happen. So what did he conclude? Well, He had to interpret all that data. And here's what he said. Look, I think all the mass and all the positive charge of the atom is concentrated at the center in the nucleus.
Until then, no one knew atoms even had a nucleus.
No, he discovered the nucleus through this very experiment, ELD. And then he said, look, the nucleus is really tiny. If I know the size of the atom, and I know how many particles went straight through versus how many deflected, then I can estimate that the nucleus is extremely small, way, way smaller than this object we have here. Look, Iber got really close to the actual size and position of our nucleus here. He figured out that this nucleus is absolutely minuscule.
If we used a scale like this, Alfredo say, if an atom were a soccer stadium, how big would the...
It'd be like a tennis ball right in the center of the stadium, of the whole stadium. But then he ran into a problem. Because, look, if you have a tiny nucleus and you already knew there was positive charge in it, then there had to be something negative too. And the person who discovered that was his boss, Thomson. He discovered the electron back in 1895. But Thomson thought electrons were scattered throughout like raisins in a plum pudding.
Or like chocolate chips in a chocoton cake.
Right. They were just spread out and stuck in there. Because he knew electrons could be pulled out of atoms, right? But now we know electrons orbit around the nucleus somehow. So Rutherford said, look, I think electrons orbit the nucleus like planets around the sun, right? The sun is the nucleus, and the planets revolve around it. He thought that model would work, but he already suspected it had a flaw. So what was Rutherford's problem, right? His model is one of the most popular ones, isn't it? Imagining electrons orbiting like that, right?
That classic drawing of an atom like a solar system with electrons circling around.
With orbits and everything, right? But it was flawed from the start. What was the problem? According to the physics known at the time, if you have an electron, I'll represent the electron with this marble. And let's say this circle is the atom with the nucleus right in the center. The nucleus is positive, so it attracts the negative electron, right?
Right.
So let's make this electron orbit around here. What was already known back then is that if you have a charged particle moving in a circle, it's accelerating and it loses energy. And if it loses energy,
eventually, it reaches the center.
It crashes into the nucleus. And that's a problem because we know atoms are stable. Electrons can't just fall into the nucleus. Rutherford's model doesn't explain why electrons stay in orbit, right?
So this is exactly what shouldn't happen inside an atom.
That can't happen, otherwise atoms would collapse. So what's the conclusion? That the physics they knew, the classical physics that had explained everything up to that point, wasn't enough. Physicists back then thought all of nature would be fully understood in just a few more years. There'd be nothing left to discover. Little did they know. This would turn everything upside down. Because once they realized classical physics didn't work for electrons, they had to invent a whole new model for atoms. And that's what we now call quantum mechanics, right?
So the rules are a bit different.
Completely different. The rules that work for marbles don't work for electrons or atoms. There are all sorts of weird things. So how did they get into this whole quantum idea and solve this problem? The next key figure in this story is Niels Bohr, right? He was a physicist who started studying what happens when atoms emit light. We've already done several videos like this on Manual du Mundo.
Yeah, like when we passed electric current through gases.
Right. Electrocuted gases. We shocked salts. And they all emitted light, right? For example, if you take sodium from sodium chloride, table salt, and drop some on the stove, you see,
it turns yellow.
You get that yellow glow. Why do these atoms emit light? How did Bohr solve Rutherford's problem? He said, look, I don't know why electrons don't fall into the nucleus, but let's assume they simply don't. And let's see where that takes us, okay? So he said, electrons orbit the nucleus, and while they're in orbit, they neither gain nor lose energy. Later, they can gain energy, like when we give them an electric shock or heat them in a flame. Then they jump to another orbit, and when they fall back down, they emit light.
Kind of like standing on a staircase. You go up one step, Then step back down.
Exactly. So we can picture it like this, right? Here's a scaled model showing the energy levels of the hydrogen atom. So what do we have here? Each orbit, where the electron circles, corresponds to a different energy level. But the electron is either in this orbit, labeled 3, or it's in 4, 5, 6, 2, or 1. Level 1 has the lowest energy. We couldn't draw it to scale. The gap between 1 and 2 is actually huge. Normally, the electron sits at level 1. If it gains energy, it jumps to 2, 3, 4, etc. But it can't stop halfway. It's just like a stair step. Even if you try,
You can't stand between steps.
you either step here or here. Same with the electron. It's either here or there. In hydrogen's case, scientists already knew about the light it emits. So, when an electron jumps from level 3 to 2, it emits red light.
Got it. So if you heat hydrogen, say in a tube, and let it cool down, it starts glowing red.
Right? Or in a lamp filled with hydrogen gas.
You zap it with electricity.
Exactly. It jumps up, and when it falls back, it emits only specific colors, just a few distinct lights. Each color corresponds to a different energy. So this small jump here matches red light. Green light has more energy, so that jump is bigger. Even bigger jumps produce blue light, and even larger ones produce violet light.
Got it. And what if it jumps from 6 down to 1, for example?
If it falls from 6, 5, 4, 3, or 2, all the way down to 1, the gap is so large that it emits invisible light, ultraviolet radiation.
And what about jumping from 4 to 3?
Then it emits infrared light, infrared radiation, which we can't see and has less energy. All jumps down to level 3 emit infrared.
Icky. So the only colors we can actually see from hydrogen are these 4 here.
Yes, just these 4. And this is where the word quantum comes from. Quantity, right? You have fixed amounts of energy. This energy is quantized. We say it can only take certain specific values, so anything that can only have certain values is quantized. And electrons...
It's like a fixed packet.
Exactly. Electrons behave this way, and so does light itself. Light comes in energy packets, and only when it absorbs a packet with just the right amount of energy can the electron jump up, otherwise it can't.
So that's quantum physics. These fixed amounts, the exact step size an electron can take.
Right. And this applies in many other ways too. For example, when atoms bond together, their electrons aren't just around one atom anymore. They're shared among multiple atoms, orbiting the whole structure. So molecules also have energy levels.
Is this diagram only for hydrogen? If I have a different atom, do the levels change? And if it's a molecule, does it change again?
Yes, if you have H2, a hydrogen molecule, the energy levels are different. That's why you get different colors from sodium, chlorine, and so on.
So is everything we see based on this? Do all the colors we perceive come from electrons changing?
Exact. Take my red t-shirt. If it looks red, it's because its electrons absorb all other colors and reflect only red light.
Wow. That's how it's all connected.
Because think about it. A marble can have any amount of energy, right? This marble up here has more energy than one on the table, doesn't it? Yes, potential energy. If I drop it, it falls, right? So here it has one energy level, and I could place it anywhere in between. It's continuous. But an electron, no, it's either here or there.
Got it. And this changes completely from atom to atom.
Exactly. It doesn't rise smoothly like a ramp.
Shall we move on? Alfredo, what's next?
All right. Here in this black box, we've made the area a bit darker. We were just talking about how molecules, like atoms, can also emit light. And some molecules emit light when exposed to higher energy light, like ultraviolet UV radiation, which is what these LEDs above us are producing. Let's turn it on.
Can I switch it on?
Go ahead, check this out. So we've got several materials here. Some dyes, for instance. This one is from a highlighter marker, very fluorescent. Here's another, orange-colored one. We also have laundry detergent. Manufacturers add fluorescent dyes to make clothes look whiter than they really are.
So that works when you're out in sunlight, which contains UV light.
And we also have some glass beads. These contain uranium, which gives the glass its color.
And Alfredo's uranium glows way better than ours. We've also got a little uranium dish here. Let me grab it. It's made of Vaseline glass, right? That's what they call uranium glass, but our little dish only glows faintly.
Interestingly, people used uranium to color glass long before they knew uranium was radioactive.
So uranium was originally just a pigment.
One of uranium's early uses was coloring glass, making this special kind of glass. In fact, radioactivity was discovered while studying uranium's fluorescence. Scientists were checking whether this glow had anything to do with X-ray emission. So, they tested it with photographic film and discovered that uranium does expose the film, but not because it emits X-rays or because it's fluorescent. It's because uranium is radioactive, and that's how radioactivity was discovered.
Now, thinking about everything we've discussed, color, atoms, energy levels, what's actually happening here?
The UV LD is emitting radiation. The dye molecules here absorb that energy. Their electrons jump to a higher energy level, and when they fall back down, they immediately emit this visible light. In this case, the electrons jump here emits green light. Here, it emits blue light, and here it emits orange light. So each one has a different sized jump.
But it seems kind of magical because it's receiving light, we can see it. It gives back light, we can see.
Right. If it absorbed all the ultraviolet energy and re-emitted ultraviolet light, we wouldn't see anything.
Let's try it. Did you bring some turmeric with you?
Yes. Look, this is ground turmeric, right? Also called curcuma. Contains a substance called curcumin, which is fluorescent. Let's see what happens when we mix it into water.
Alfredo, that didn't work out so well, look.
It's not very impressive.
We've also got this stuff from that time we did an experiment with a toilet flush to see if flushing releases droplets. And we discovered it actually does. It was a really cool experiment. But this fluorescent dye is super strong. It's almost brown, kind of weird. Looks like coffee.
It's too concentrated.
But as soon as you pour it,
well, Bohr. Besides fluorescent, which we just saw is super cool, there's another phenomenon where materials absorb light, ultraviolet radiation, and then emit visible light. That's phosphorescence.
Got it. So phosphorescence is fancier than fluorescence, more surprising.
It's interesting because it's different. Look, we've got a phosphorescent material here. This is a sticker we placed. When you look at it under UV light, it seems like the same thing, right? It looks like it's glowing. But now put your hand over it. Now let's turn off the UV light. Take your hand away.
Whoa! The light stays on for a while.
Exactly. Where it received light, it stored that energy and keeps emitting it for a while. So all those materials we say glow in the dark, right? Those are phosphorescent, not fluorescent. So Bohr, there are many types of phosphorescent materials, right? And they come in different colors. We're used to that greenish glow, right? You know, those toys, the planets and stars you stick on your bedroom ceiling. But they actually exist in many colors.
So you're charging them, right? When they're near light, it's like they're storing energy.
In this case, the electrons all jump to a higher energy level. And after that, they fall into an intermediate level. That intermediate level comes from an impurity added to the material. And that impurity is what they call a trap. It holds onto the electron can't escape right away, so it takes longer to release. So with fluorescence, the electron jumps up and comes back down instantly. But with phosphorescence, the electron jumps up, then gets caught in a trap. And even after you turn off the light, it keeps glowing. Go ahead, turn off the room light so we can see.
Wow, you can really see it.
It keeps glowing for a while.
Look in the dark. Oh, it's really dark. Let me charge it close to the UV lamp. Look, you can even see the shape of the lamp imprinted.
Each one uses a different material and a different impurity. That's why they emit different colors.
This one's really cool. Are these tiles meant for walls?
No, I made these with resin and that phosphorescent pigment.
So we can make these at Manual do Mundo. Look, this is the pigment Alfredo used for these little tiles. I'm going to test it with a UV laser. It's way stronger than the UV light up there. Check this out, man. Now with the laser, we can clearly see the difference between fluorescent and phosphorescent. Here's the uranium glass. This one's phosphorescent, it stores the light. The fluorescent one glows but doesn't store anything.
As soon as the light goes off, it turns off.
Look how beautiful. Even the laser beam leaves a glowing trail.
Yeah, that looks great. And another interesting thing, it depends on the color of the light. If I use red laser, nothing happens. Why? Because red light doesn't have enough energy to make the electron jump in these materials.
Right, it has to be high enough energy so that even after spending the emitted light is still visible.
Exactly. Now here's a fun activity. Using phosphorescent material. I took a CD and sprayed it with phosphorescent paint. And I 3D printed
a top.
A little stand here so we can spin the CD like a top.
So I just draw on it with the laser.
Yeah, go ahead and zap it.
No. Dude. Oh wow, this is the moment. Man, I haven't seen this experiment before.
This one's definitely a thumbs up.
It's so cool. Look how pretty. Alfredo, I could stay here for days playing with this thing.
Yeah, it's awesome. And you can do tons of experiments with a spinning top, right? You can use phosphorescent material, or you can use multiple colors and see them blend into white when spinning.
Yeah. Make a Newton's color wheel, man. So beautiful!
And if you don't have a laser, you can just use an LED.
A blue LED, right?
A blue LED or UV LED. So I brought you a practical application of quantum mechanics LED. Something real. Not just lab stuff. You know, fluorescence and phosphorescence are already super useful, but a truly practical result of understanding how materials absorb light and how atoms are arranged using quantum physics is the creation of solar panels. So, I brought this little model house.
A tiny house with a solar panel on top. With this lighting, it's pretty dark here because of the previous experiment. Yet the LEDs inside the house are lighting up. There are blue LEDs in there that are turning on.
Right, but we don't just have LEDs. We've also got a little fan, a motor, right? I don't think the studio light will power it, but let's try turning it on.
And it's Alfredo. Before you grab a brighter light, just explain what's happening in the panel and how it relates to what we've seen.
So this panel, it's made of silicon. Silicon is neither a full insulator nor a good conductor like metals. It's a semiconductor, right? So when they manufacture the panel, they take silicon and replace some of its atoms with other elements. Some with fewer electrons than silicon, others with more. It's all layered like a sandwich. There's a conductive layer, silicon with extra electrons, silicon with fewer electrons, and a transparent conductive layer on top. When light hits it, electrons gain energy and climb the ramp, so to speak, LD. They gain energy and generate an electric current. With that current, we can light an LED or spin a motor just like this.
So it's like the electron is actually walking up that staircase we saw earlier.
Exactly. And it hops from one silicon atom to the next. Because those holes and extra electrons can actually move through the material. And that creates a usable electric current that can power things in our homes.
Yeah, but it needs a lot of light, which we don't really have here. Time for some manual do mundo ingenuity, Alfredo. We're making this work one way or another.
Do you have a strong light ready?
This light here, I think it's not strong enough. Will this little fan spin? Oh, it's even moving the whole thing. Look. Awesome, Alfredo.
I think this video showed us a ton of cool things. And I hope you all got the main idea. We can use 3D printing to build lots of useful educational tools for school.
Exactly, they're learning objects like globes or whiteboards, and things we use to understand concepts. And with a 3D printer, the possibilities are practically endless.
You designed many of these yourself?
Yes, some we created. Others we found ready-made and adapted. This project for the International Year of Quantum Science done with the Brazilian Chemical Society. Was funded by CN. We got the resources to build these models, created this exhibit, and showed it at many events. Many of these very models and explanations for all these experiments are on our website, xciencia.org. It's a website created with resources specifically for teachers, especially chemistry teachers. So we've brought it here to Manuel do Mundo.
I really hope people can now see quantum physics in a more accurate light, right?
Exactly. It's something that only deals with atoms. There's no such thing as quantum healing or quantum consciousness. Just a bunch of scams.
And I'll leave a playlist at the end of this video with all the videos I've already recorded with Alfredo. He always stops by Manuel do Mundo to show off some really cool experiments. From the chemical cupcake way back in 1900 and something, back when you could still tie up a dog with a sausage, to the electrocuted gases we filmed about 2 years ago, more or less.